In this video, we are going to discuss on DC machines, where we will see by the end of the submodule unit, the trainee should be able to achieve the 7 objectives. Number 1, describe the construction of DC machines. Number 2, explain the principle of DC machines. And then number 3, describe the classification of DC machines. Number 4, describe the operation of faceplate starter. Then number 5, explain the armature reaction and commutation. And then number 6, describe the characteristics of DC machines. And then number 7, lastly, you said that the trainee should be able to state the application of DC machines. We use a reference of John Bird, that is Electrical Circuit Theory and Technology of Routledge of the 5th edition. Then under construction of DC machines, it has a number of parts. We have the yoke, the main poles, the field or the magnetizing coils, the armature, the commutator, the brush gear, and the bearings. You need to know how each part or the function of each part. Then you need to know the principle of operation of the working of DC machines. Then you need to, when we classify DC machines, we look into separately excited DC machines, self-excited DC machines, long compound, short compound, that is under the classification of DC machines. And then we look at the faceplate starter as a method of starting DC machines. You need to know the need for the faceplate starter, the protective devices involved in the faceplate starter, and the operation of the faceplate starter in DC machines. And then another point was on the armature reaction. You need to know what armature reaction is and commutation and what they are involved in DC machines. Then you need to know the characteristics of DC machines, the characteristics of generators, and the characteristics of motors. And then lastly, the application of DC machines. Then moving to our content on the introduction of DC machines, we have when you want to know the conversion of DC machines, it can either be mechanical to electrical or electrical to mechanical. So an electrical machine continuously converts electrical input to mechanical input or mechanical input to electrical input. The process of translation from mechanical to electrical or from mechanical to electrical or from electrical to mechanical is called electromechanical energy conversion, which is reversible. You can reverse. You can do electrical to mechanical or from mechanical to electrical, as we have seen earlier. Then when you want to convert from mechanical to electrical, you use a generator, as compared to converting an electrical to mechanical using a motor. You will see how the characteristics of a generator are and how to convert the mechanical to electrical. So we have primary quantities in electrical systems and mechanical systems, where in electrical systems, we have voltage and current. Those are the primary quantities that are used in electrical systems. I think we know them. That is, we have the voltage denoted by V or E as an EMF or as a potential difference. Then we have the current I. While the analogous quantities or the equivalent quantities of voltage and current in mechanical systems, we have torque and speed. Torque denoted by T, speed denoted by N. So from our figure here, you can see we have electromechanical conversion. That is the electrical machine. And then in electrical systems, we have E. In electrical systems, we have the voltage E. So in electrical systems, we have E, this one, the small e, and then we have I in electrical systems, that is the current. While in mechanical systems, we said we have torque denoted by T and speed denoted by N, torque denoted by capital T. In electrical systems, we have said we have voltage and current. So when you want to convert from electrical to mechanical, Electrical to mechanical. So we have electrical to mechanical, you use a motor. Electrical to mechanical, you use a motor. And then from mechanical to electrical, you use a generator. You use a generator. That is when you want to convert from electrical to mechanical, then from mechanical to electrical. That is the electromechanical energy conversion. So moving to the next figure, we have a coupling field. I have a coupling field. That is the coupling of magnetic fields from electrical to mechanical and from mechanical to electrical. You can see the direction of arrows. The direction of the arrows show how you convert from electrical to mechanical and mechanical to electrical. So moving to our next point, we have we have the basic structure of electrical machines. So in electrical machines, we have the stator and the rotor. We have the stator. We have the stator in electrical machines. We have the stator. We have the stator and the rotor. Sorry for that. We have the stator and the rotor here. The stator and the rotor. The rotor is the stationary part. The rotor is the moving. The rotor is the moving. Where is the stator? The stator is the stationary. The stator is the stationary. It does not move, and it's normally the outer part of the machine. The stator is the outer part of the machine, which is stationary, while the rotor is the moving part or the rotating part of the machine. So in cylindrical machines, it has a uniform air gap. In cylindrical machines have a uniform air gap. You can see from the first drawing or from the first figure, we have uniform air gap. While in the second diagram, that is part B, we have different. We can see the difference between the rotor and stator. The rotor and the stator have an ununiform air gap. That is a salient pole machine. So the stator in electrical machines, the stator and the rotor are separated by the air gap. So we have the rotor and the stator. You can see from the two. The rotor and the stator. We have the rotor and the stator. So these ones have an ununiform. We have non-uniform. These ones have a uniform air gap. These ones have a uniform air gap. These ones have an uniform air gap. You can see from the two diagrams, you can differentiate. So moving on to the next point. We have classification of electrical machines. So when you classify electrical machines, you can classify them into three. We have direct current machines. We have the direct current machines. The electric current machines have DC both in stator and the rotor. They have DC current in both the stator and the rotor, while synchronous machines have AC winding in the synchronous machines, AC in one winding, that is in the stator, while the rotor has a DC winding, has a DC current. So in induction machines have AC in both the rotor and the stator. You can see from our diagram or from our table 1. This is our table 1. These are the configuration of the three types of electric machines. So we have said DC has a winding type of armature, while the other part, that is the magnetizing, has the field. Rotation, we have the armature windings are found in the stator, the field windings are found in the stator. Then the current is we have DC as the brushes and the AC in the windings. So in the stator we have DC current. So in synchronous machines, we can see the winding type, we have the armature and the field. Where we have the armature windings in the stator, The field windings are found in the rotor, which is the moving part, and the current found in the rotor is DC, while the current found in the stator is AC. So moving to our next classification of electrical machines, we have induction machines, where we have the input, the output, that is the winding type. The winding type is either primary or secondary, where you have the primary in the stator and then the secondary in the rotor. The secondary in the rotor, where the current is both AC and AC. That is the stator in the rotor as AC current. So moving on to our next slide. Moving on to our next slide, that is on the action of a commutator. Under the action of a commutator, we want to consider a single loop conductor, conductor that is mounted between two magnets. We have a magnet. A magnet has two poles. We have the north pole. We have the north pole and the south pole. That is a magnet. A magnet has a north pole and a south pole. So we have the voltage. A voltage is applied at 2 points, A and B. We'll see that in our next diagram, where the voltage is applied between points A and B in our next figure. Then we have a force of F. A force of F acts on the loop due to interaction of the magnetic field of the permanent magnets. So this is our magnet. That is, a magnet has a north pole and a south pole, as we have seen earlier, a north pole and a south pole. Then we have A and B. Between points A and B, we apply a voltage. Between points A and B, we apply a voltage. And then we have a force F. We want to apply a force F on the loop due to the interaction of the magnetic field on the permanent magnet, and therefore the magnetic field caused by the current I flowing in the loop. So this force F, the force F that we have applied in our between the two permanent magnets, is directly proportional to flux density denoted by B, and directly proportional to current I and the length L. So therefore force is equal to the flux density multiplied by I multiplied by L. That is our formula to calculate force in our conductor. So in the force has two parts. That is, the force now we have discussed has two parts. Using the Fleming's left hand rule, using the Fleming's right hand rule, the first force acts vertically downwards due to current flowing from point C to point D. And another force acting vertically upwards, due to the current flowing from E to F. Due to the current flowing, you can see that from our figure 1.4, part M. So if the loop is free to rotate, if this loop is free to rotate, that is our single loop conductor is free to rotate, then when it has rotated through 180 degrees, the conductors, when it rotates through 180, we have a resultant of part B. We have that a resultant of part B, where for the same rotation to continue, it's necessary for this current to flow from D to C. You can see that from D to C, and from F to E. You can see that from F to E. So you can see that so we have point A and point B. Then you said you apply a voltage through A and B. You apply a voltage through A and B. And then we have a current flowing from C to D. Using Fleming's left-hand rule, we have a current flowing from C to D and E to F from our figure 1. Then when it has rotated through 180 degrees, we have a resultant of figure B, where we have a current flowing now from D to C and a current flowing from F to E. So that is to have a continuous rotation or for it to move in the same direction, the current must flow from D to C and then F to E, as we have seen from the diagram there we had. So for this apparent reversal in the direction of current, it's achieved by the process of commutation. Therefore, commutation is the reversal of the direction of current, the reversal of direction of current flow. So in our figures, we have a different figure here. We have figure 1.5. So when a direct voltage is applied at point A and at point B, when a direct voltage is applied through point A and B, you can see here, point A and B, the forces act to give a continuous rotation in an anti-clockwise, this is an anti-clockwise direction. So the voltage is applied to the rotating segments by stationary brushes. We have the brush here. We have brushes. This is our brush. So those are stationary brushes which slide on the commutator material. This is the commutator, the two segment commutator here. We'll see how to draw the segments differently so that they can be visible. In our next video, we'll discuss on commutator segments. So poor commutation results in sparking. Poor commutation results in sparking of brushes. So this can be improved by using interpoles or high resistant brushes. You are using the brushes spanning several commutator segments. So poor commutation results in sparking. So to avoid the poor commutation, you use interpoles or high resistant brushes or using brushes spanning several commutator segments. So here in our figure B, we have a commutator segment. We have a single or multi-loop. Then we have a single or multi-loop conductor. Then we have the brushes. These are the brushes we have seen here from our figure 1. These are the brushes. These are the commutator segments. We have around 1, 2, 3, 4, 5, 6, 7. We have 7 commutator segments in this section. So we have 7 segments in that section.